Am I recording? Oh, I am recording. Oh, okay. So, hello all. This is me redoing what I did yesterday because the audio and the video did not sync together. And so I wanted to make sure to re-upload it in order for you guys to get everything you need to know. So I'm going to skip over this bit because I feel like I'm going to leave up that old video just because I don't want confusion. But in all, I'm going to just say that welcome back. My office hours have changed. That's apparent on the slide. These slides are posted on Blackboard, so if you need to know that information, it's always going to be posted for you. And please email me. I loved getting responses about the video, and especially the response that this was not working. So please let me know those things. I don't want you to feel like, oh, well, she doesn't know how to use computers, and therefore we are screwed. So please reach out to me when things like this happen so I can then do this, where I can re-record it and make it better. Awesome. Okay. So that's that. All right. So AcidBase Equilibria. AcidBase Equilibria is basically looking at how acids and bases work. So you are still using equilibrium constants. A lot of people find a disconnect in these two things. They like to say, oh, I'm doing acids and bases, and therefore they kind of throw all of their equilibria knowledge out the window. Please do not do that. These are literally the same thing. Ka is, of course, the equilibrium constant for acids, and Kb is for bases. And what that means is that the A for acids is that there's going to be a hydronium ion in your products. You are making hydronium ions, and that is what is decreasing your pH. So the higher concentration of H plus means a lower pH. Acidic pHs include 1 up until like 6. 6 being very weak, but still an acid. And then the same for Kb, you're going to have OH minus in your concentration because the POH is how you relate to pH, and that if you have a low pH, then you have a high pH, and a high pH is basic. Replay this if that didn't make sense. That was very quickly said. And I know it seems obvious, but I know that this can get very confusing because things are so inverse, and it's that negative log part. And again, K values are dissociation constants, so a weak acid does not completely dissociate, unlike a strong base and a strong acid, which is what these titrations are hopefully going to show you and kind of prove that fact to you. And because of that, that means that weak acids and bases love to use ice tables because we are trying to find the change when we add something because it doesn't completely dissociate. So there is going to be molar ratios that need to be taken into account and the different molarities that we start with. So please, I know we don't like ice tables, but they are important, and the quicker that we learn to accept them, the better. Okay, so now when can we ignore X, and when is, that sort of happy medium where, there's a fine line? And that's what I like to call the 5% rule. And the 5% rule is the math way of doing it. And I like the 5% rule because you have a solid cutoff between them. And that is when you take X, remember that change line, so how many moles you're adding or subtracting to it, that divided by your initial concentration. So if you're doing it in concentrations, then keep them all in concentrations, etc. Moles do moles. Underlining being that if you take that X divided by the initial concentration, if that is less than 5%, then you're okay to ignore X. If it is greater than 5%, then you should not ignore X. Now, what I mean by that is if I tell you have 0.25 molar of something in your reaction flask, and then I tell you that X equals 0.0095. Well, when I take the 5% of 0.25, that is 0.0125, which means that the 0.0095 is much less than that, and therefore we can ignore X. Okay, so that is something that you should be careful of because there was a hydrofluoric acid question on your homework that I know did test this theory about whether you can ignore X or not, and in that case you should not have, because the 5% rule showed that the initial concentration when you took X divided by that was greater than 5%, and therefore X should have been included in that equation. So it is important to know when you are supposed to ignore X and when you shouldn't. Okay, and then so this overall lab is basically a strong base, strong acid lab to show you the equilibrium when you have a strong base and a strong acid, and then it's a strong base with a weak acid. And the reason for that being is that you have a time in when a strong base is being titrated against a weak acid, that you have a buffering zone, and that buffering zone is specifically when the weak acid is getting heavily influenced by the strong base because the strong base is completely dissociating and making a lot of that conjugate base. However, the acid is still directing that pH towards the acidic side until you pass equivalence point. And then another thing to note is the calculation. So your calculations are all going to be a lot of calculus, specifically first and second derivatives. And the reason for that being is that you'll notice at the equivalence point, the slope of that line right there is 0. And therefore, we look at the first derivative to see the max, and then the second derivative to see when that line crosses 0. And when it crosses 0, that is when you know that is the amount of volume you have, when you can then work backwards with your pH to then find the unknown concentration. So it should be a very simple, straightforward thing, but sadly, acid and bases never are, and so that's why I expect you guys to email me if you have any troubles with this lab, especially calculations, because I know those can be very confusing, especially when you are just given a data set. Okay. So the other thing is that you are pointedly going to be doing a titration of a strong acid versus a strong base. And because these are strong acids and strong bases, the NaOH, you're going to find your equivalence point is about 7. And that is because this is when those two are neutralized, because you have your acidic zone here at about 1, and then you'll see that as you add more base, you slowly go through equivalence point, and then you reach a very basic zone. But that is very different in comparison to a weak acid versus a strong base. Emphasis on weak. And that is because when you have a weak acid with a strong base, you're going to have a buffering zone. Like I said before, this is when you have a little bit of that acid that is still fighting to keep it acidic. And that is sort of why there's a little raise, because that's the base immediately taking over, but then the acid sort of buffers. And that's why also our equivalence point is now past 7, because technically that strong base has taken over and made it so that we now have more of this basic range when we find our pH, because the strong base is beating the weak acid in a sense and making that equivalence point happen at 8. Now I'm going to show you if you had a strong base versus a strong acid. So in this case, let's say that we, instead of having a strong acid, we have NaOH and we're titrating NaOH, in this case the base. And instead of titrating NaOH, we're instead going to be using something like HCl. So I'm going to write that down. I'm very slow because I can't write. So I have HCl. And you'll see that there's an inverse of that here. So I have an inverse shown on the graph. Right now I'm just writing that over there, but focus more on this strong base, strong acid stuff, and that I basically just flipped it. So now I start basic. My equivalence point still goes through 7. Now, when I'm drawing this again, you'll notice that there is still that buffering zone that happens if I had a weak base. And that's where the strong acid immediately takes over and makes a very quick jump in the pH, only to then even back out and buffer for a bit before going through the equivalence point and reaching its basic pH. So they're still in the same place. So please keep that in mind, that there's still that buffering zone that happens in the beginning. However, you still end in your basic or your acidic range when you have your acid. So that's still very much true. All right. So, well, do I have something else I wanted to say? Oh, not yet. Okay, perfect. Half equivalence. Oh, this one. Half equivalence. So half equivalence is basically when you have halfway between the origin and the equivalence point. And when you're halfway between the equivalence point and your origin, you'll find that your pKa is equal to your pH, which is very true when you are doing a weak acid versus a strong base, but you can also find the same thing with a strong base and a weak acid. It's just that you'll be looking at your pKa as if it were a base. And I know that can be slightly confusing, but it's still the same rules apply. It's the pKa that equals the pH. And the equivalence point is when the moles of the titrant equal the moles of solution with an unknown concentration. And this will be evident when you have a strong acid versus a strong base, and that will happen if you have the same molarities and then the same volumes, that then you will find that happens very much so when they have equal amounts and it's more obvious. But then when you're changing the molarities or changing the volumes, that's when it's not as obvious. So make sure that you note that in these examples that I'm about to show, I'm using the same molarity to calculate these. So that's why this is a bit more straightforward. And I will do harder problems later on when you guys are more ready to do that. Okay, so this is a titration carried out with 25 mils of 0.1 HCl, and that's a strong acid, and then also with 0.1 molar of a strong base. So when I'm calculating the pH, I'm going to be looking at this kind of titration graph where it's a strong acid versus a strong base. So I first want to know the concentration of hydronium ions because that's going to tell me my pH. And then I'm going to look at the moles of H plus over the total volume. Now that moles of H plus is not exactly the concentration, but it's the moles of hydronium ions from HCl neutralized, aka minus the moles of OH minus. And I'm going to get those moles from taking the volume, converting it to liters, and multiplying it by its molarity. Cool. So here we go. This is this many moles of H3O plus and the moles of OH minus. And you'll see here that I get 0. And a lot of people are like, 0? Well, we can't have 0. If I have 0, negative log of 0 is 1, and that's not what's going on here. I know that the equivalence point does not happen then. And I also know it's been neutralized. And so what I then can realize is that if they equal each other, then it's water. And I'd use Kw is 10 to the minus 14, and therefore the hydronium concentration is 10 to the minus 7. And then if I look through, I'm going to use the concentration, negative log of the concentration of hydronium to get my pH. Now this should look very familiar because if I go back, keep going back to my graph, that's where I expected my equivalence point to be. So that makes good sense to me. All right. Now, that was at equilibrium, but what if we're not at equilibrium? And so this is when I have less of the strong base. So I have less base this time because before it took 25 mils and now I'm before that. So if I go back to my chart, I'm going to find that at 12.5 mils, I should expect a somewhat acidic pH. And so then if I go forward, I'm going to use the same, I thought I whizzed through that. I'm going to do the same sort of calculation, but I need to keep in mind that I have 12.5 mils of strong base. So then I have my molarity times the liters, but of 12.5, and then my total volume has also changed. That equals 0.033 moles of my hydronium ions, and then I plug it into the same equation that I had before. Negative log of the concentration of H plus, and that again gives me my pH. 1.477. Again, this makes sense to us, right? Because I have not reached the equivalence point yet, so I am still at that point where the strong acid is in control, and I have not added enough base to reach equivalence. So that makes good sense to me. Wonderful. Okay, rolling through. All right, the titration curve is with now a weak acid and a strong base. Cool. I'm going to write out my equation here. I know that I have a base, and it's asking me what the initial pH is before any amount of NaOH has been added. So I'm going to look at my Ka here, and it's going to have H3O plus and my acetic acid, so my conjugate base, over my HA. Now, this is because when I look through here, no NaOH has been added. If no NaOH has been added, then no conjugate base has been made, because if I look at my equation, we need OH minus to get our acetic base conjugate acid, or conjugate base. And so instead I just have to look at the initial concentration of my acid, and then I go through, my Ka times that initial concentration will equal hydronium ions squared. Again, hydronium ions squared because we only have hydronium ions in here. And then I use my Ka that's given, I plug that in, I get that my concentration of my hydronium ions, and then I plug the concentration into my negative log to get my pH. My pH is about 3, and that kind of makes sense. The reason the pH is about 3 is because this is a weak acid. There we go. A weak acid, and a weak acid would be at about 3 to about 6. Those are considered weak acids. Weak bases are about 12 to 8. So that makes good sense to me. Cool. All right, that final part. We're going to find the pH after we add 25 mils of 0.1 moles of a strong base with our 25 mils of weak acid that we already have in our reaction flask. before that 25 mils neutralized this solution, now we're going to see if it's neutralized or if that pH is going to be slightly higher. Spoiler alert, it's probably slightly higher. All right, so that NaOH we're relating back to our problem, and we see it's a 1-to-1 mole ratio with our conjugate base. That makes good sense, so we know that we can use the concentration and the volume of the NaOH to then equate to the concentration of our conjugate base. Then we're going to set up our Kb. Again, Kb would be the conjugate base is going to be our reactant, and then of course our OH minus concentration is going to be a product as well as our acid. So that's going to be in our products. And then we take that Kw equals Ka times Kb, rearrange that equation, we know what Kw is, and we get Ka from the problem, and we'll get 5.6 times 10 to the negative 10, I'm sorry, there's a typo there, and I plug that in. So my Kb, we have unknown values of our acid and unknown concentration of OH minus over our known concentration of our conjugate base, so we plug that in. Ooh, plug that in, no, plug that in, plug it in, perfect. And then I get x squared over my concentration of acetic or my conjugate base to get my OH minus concentration. So that means I'm going to use POH. Remember, this is an OH minus concentration. So my negative log of OH minus is going to give me POH. They will definitely try and trick you with this. So remember, don't trip up on the last leg. You get POH. POH equals 14 minus pH, and therefore your pH is going to be 8.72. Now this makes sense because as we look back to our graph, 8.72 is about where we expected our equivalence point to be because it is a weak acid with a strong base, and therefore to neutralize it, it's going to come at a more basic pH, as it's going to take more effort to completely dissociate that weak acid. All right. Hope you guys had fun. I hope this video was enjoyable. I hope it was helpful. Let me know what wasn't working, what did work, and we'll work on it for later. Other than that, I hope you guys have a wonderful day, and I'm sorry for the delayed video before.